In this video, we're going to look at the modulus function. We write the modulus function f of x now as the modulus of x, and we have modulus bars. For short, we call this mod x, and sometimes you might hear it being referred to as the absolute value of x. The algebraic definition of the modulus of x is that we have now x if now x is going to be greater or equal than 0, and we have minus x if x is going to be strictly less than 0. So this now is our algebraic definition. If we put this simply now, the absolute value ignores the sign. So if we have a positive or negative, we simply consider the magnitude of the number. If we look at that on a calculator, our absolute value button here, if we do the absolute value of minus 8, we get 8. The absolute value of 9 is going to give me 9. An alternative way to picture this is on a number line and consider the geometric definition. So if I drew up a number line like so, we could have now the origin just here. So if we think of this as the x-axis, so we've got the origin just here, and we took now minus 3, and then we took positive 3. The distance from each of these numbers to the origin quite clearly is 3. So we can say now the mod of 3 will be equal to 3, and also the mod of minus 3 will be equal to 3. So all we're looking at now is the modulus as the distance now from the origin. So that is 3, and also that is 3. So in general, if we have the point now x just here, and we have a positive value of x, and then we have negative x, we can say the modulus of negative x is going to be equal to x, and then the modulus of x will also be equal to x. Let's go ahead and look at the graph. So what I'm going to do is graph y is equal to the modulus of x. So what we're going to do is consider this definition right here. If I think about the graph to the right of the origin, I'm going to have the line y is equal to x, as we can see here. So this is what I call my positive branch. So this is y is equal to x. When I'm to the left of the origin, I'm going to have minus x. So we can see now that this only yields positive values. So to the left, we've got now y is equal to minus x. So we can say that this is going to be now y is equal to the modulus of x. The domain is all real numbers, so we can put all real numbers in. So x belongs to the reals, and the range, we can write the range now. We will have y is going to be greater or equal than 0. This won't return a negative number. So what we have here now is, on the negative part, a reflection in the x-axis. So if I just put this up, the original line y is equal to x now was coming down here, but as soon as this was negative, we reflected it in the x-axis to get the line here. In the video, we're going to look at two different types of graph involving now the modulus function, and also go on to solve equations and inequalities that include the modulus sign. So let's start off with some graphing. What I'm going to do is look at the two particular graphs that we might be asked to focus on. The first one is y is equal to the modulus of the f of x. The next one is y is equal to the f of the modulus of x. Now we need to distinguish between the two. Let's start with the first one. With this particular approach, we evaluate the function. Any negative value we get as a result of putting a number through the function, we make positive. As a result, when we graph this, it's a reflection in the x-axis for any negative point. So let's go ahead now and graph y is equal to the modulus of 2x minus 1. So this is of the type y is equal to the modulus of the f of x. So here is the f of x, and it's inside the modulus bars. So what I'm going to do is go ahead and graph this up. So to the right of the origin, we're going to now have the positive part of this line. So 2x minus 1 is going to look something like that. Now before, what we would do is come through like so. But as soon as I hit the x-axis, I reflect this upwards. So we're going to have now the point here. This point down here was going to be when x was going to be equal to 0. So if we consider if x is equal to 0 just here, then we would get now minus 1 normally, but this is going to be 0, 1. This point is going to be 1/2, 0. So this side we've got y is equal to 2x minus 1, and this is the positive branch. We now have the negative branch, and this is going to be y is equal to minus the quantity 2x minus 1, which you might want to write as y is equal to 1 minus 2x. So when we have now y is equal to the modulus of the f of x, any time that we're going to have a negative output, we make it positive. So that's a nice example here. Let's do another one. Let's say y is equal to the modulus of x squared minus x minus 6. So the first thing I want to do is factor this. So y is equal to now the modulus of x minus 3 multiplied by x plus 2. So again, we have the first type. So if I sketch this up, what we're going to have is the following. So we'll have now a quadratic. Before, the quadratic would have gone through the point here at negative 2, and then we would have had positive 3. So we'll come round, we'll come through, we'll come to a minimum point just here, and then we'll come back up, and it'll look approximately like that. So this is now the point minus 2, and this is the point positive 3. We've got now 0, minus 6. When we have an absolute value function, we don't have any negative portion. So we come down, as we would before. As soon as it's negative, we reflect in the x-axis. It's going to come round, and then back down to this point, and then back up. So what we have now is the point just here, and that point is going to be now 0, positive 6. We call these cusps, and we don't now straighten these out. We leave them as they are. So what we've got here is the positive part. So this is a positive part, and now this is a positive part. So we could say that y is equal to x squared minus x minus 6. Here we've got the negative part, and here we've got the reflected negative part. And we can say that those are y is equal to minus the quantity x squared minus x minus 6. And we know that that's now a reflection in the x-axis. So that's a nice example now of showing a linear and a quadratic function when we've applied y is equal to the modulus of the function. Later on we will go on and see how we can use these graphs to solve equations. Let's go ahead now and look at the second type. This is y is equal to the f of the modulus of x. This time, whatever value we put in for x, we make positive before evaluating it through the function. So in the last one, we evaluated the function as it was. If it gave us a negative, we made it positive. We're making our value of x positive before it goes through the function. As a result, this gives us now a reflection in the y-axis. So let's go ahead and look at this function right here, and we will now apply this particular approach here. So what we've got is y is equal to x squared minus x minus 6. So that's the original function. So if I write this now as y is equal to f of the modulus of x, we'll have y is equal to, and then we'll have the modulus of x, which we square, minus the modulus of x minus 6. So let's think about what we had before. Now when we had this before, we took now the values and we graphed our parabola. Our parabola went through now at minus 2, so let's put minus 2 there, and 3. We had a minimum point. The minimum point was somewhere down here, and then we come back through. So that point was 3, that now was minus 2. So if we just consider, if I did now f of minus 1, this would be the same as doing the f of 1. If I did now minus 2, so f of minus 2, I'm going to get the f of 2. As we can see, every value I take now to the left of now the y-axis, I may as well have taken from the right of the y-axis, or a positive value. As a result now, we end up with the quadratic coming now symmetric about the y-axis. So this now is what we'd have. So this point is going to now be negative 3, 0. This point is going to be 3, and we would end up now with something that looks like that. So this now is the function here. This is y is equal to now the modulus of x, which we square, then the modulus of x subtracted minus 6, and that's what we have. So this is a reflection. So let's look at the difference between the two. We evaluate the function. If it's negative, we reflect it. With this one, we make all values positive, then evaluate. So reflection in x, reflection in y. We don't leave the original function there. So right now, when I drew this, I would remove now the original, and then I would remove the original from here. If you want to leave now a dotted or broken line, you can do, but certainly don't leave the original. So if you wanted to show the original curve, you could do something like that and that on this one. I generally wouldn't. I would simply now draw the original, see what the new one looks like, and then go ahead now and just graph the modulus functions. What we're now going to do is look at solving some equations and inequalities involving the modulus sign. Let's start off with the first example. Let's go for now the modulus of x minus 2 is equal to 5. So what we're doing is solving for x. Now when we solve these modulus equations or inequalities, there are a range of techniques we can use. If both sides are always positive, we can use an algebraic approach by squaring both sides and solving for x. Let's just first look at now the modulus of x minus 2. If we have now the modulus of x minus a, we can see this now as the square root of x minus a all squared. So if we look now, I could write this if I squared both sides as x minus 2 all squared is equal to 5 squared. Just out of interest, if that number on the right hand side in the equation is a negative number, it makes no sense. This is always going to be 0 or greater. It's the absolute value. So there'd be no valid solutions there. So let's go ahead and solve this. X squared minus 4x plus 4 is equal to 25. Stepping ahead of myself there. Subtracting 25 from both sides, x squared minus 4x minus 21 is equal to 0. So let's go ahead, x minus 7 and then x plus 3 is equal to 0. So we can see from here that x would be equal to 7 and x would be equal to 3. Now, do these solutions work? Well, let's try 7. 7 minus 2 is 5. The modulus of 5 is 5, so 7 works. So if we look at this, apologies, that should be minus 3, shouldn't it? If we look at this, we've got minus 3 now. Minus 3 minus 2 is minus 5. Is the modulus of minus 5 5? Yes, it is. So both of those work. One way you might want to think about it now is the difference between this number and 2 is 5. That's one way that you could read it. The difference between x and 2 is 5. And we can see from here. So we could say that 7 minus 2 is going to be equal to 5. Minus 3 minus 2, when we take the modulus, is going to be equal to 5. So that's the first way. So it's an algebraic approach when we know both sides are positive. An alternative approach would be to graph these particular lines. We graph the lines when we can say that one of the sides is not always going to be positive, and we will show that shortly. So let's look at two lines. The first line I'm going to look at is y is equal to 5. So here's the line y is equal to 5. So let's go ahead and label that. So now I'm just saying y is equal to 5. Let's now look at the modulus of x minus 2. And this just has to be a rough sketch. It doesn't have to be immaculate. It will look something like so. So what we've got is something that looks like that. Now, if we consider, and I'll just put this on, this is going to be y is equal to the modulus of x minus 2. We can see that we've got 2 points of intersection, and we can go ahead and solve them. This is the positive branch, and this right here can be given as y is equal to the positive x minus 2. So we get x minus 2, and this one here is going to be the negative of x minus 2. So let's call this solution number 1, and let's call this solution number 2. So for solution number 1, we've got now minus the quantity x minus 2 will be equal to 5. And then for solution 2, we're going to have now the positive. So we'll have x minus 2 will be equal now to 5. So if we solve this, we've got minus x plus 2 is equal now to 5. So if we subtract 2 from both sides, minus x is equal to 3 dividing both sides by -1, x is equal to -3. So this one right here corresponds to x is equal to -3. So we've got that one done. If we look at this one, just adding 2 to both sides, x is going to be equal to 7. So that's that one. So we've solved it graphically. I've taken the line y is equal to 5. I've taken now the line, or the two lines here, y is equal to the modulus of x minus 2. And we simply looked at the points of intersection. Okay, so what if this was an inequality? Let's say we had now the modulus of x minus 2, and let's put that there, is going to be greater or equal than 5. We have two approaches. If we pick this up just here now, what I could say here is that x minus 7 multiplied by x plus 3 is going to be greater or equal than 0. Now if we did this, we could draw now a quadratic inequality. So what we'd have is the following. If we had now the quadratic inequality, we would have now this point just here, which is minus 3, and then we'd have this point, which is positive 7. So drawing our quadratic, it'll look something like that. So we got now on the number line, we've got 7, we've got 3, and we say to ourselves, where is this going to be greater or equal to 0? So we've got greater or equal to 0 just here, and we've got it just here. So we could say that x would be less or equal than now negative 3, so let's just put the negative on there, and then x is going to be greater or equal than 7. If we wanted to know where this was going to be strictly less than 0, we could consider these points right here. So we could say in that case that x would be strictly greater than minus 3, yet in turn strictly less than now 7. So that's how we could solve an inequality. Alternatively, if we consider the inequality now and just read what this is saying, this is asking me now, when is the modulus of x minus 2 greater or equal than 5? And if I shade this on, what we're going to have are these points just here. So we're asking now when this line is below our modulus, and that's those parts right here. So we would just solve as we have and then just go ahead and use the graph. If we had it the other way round, if we now said that we had the inequality and we had the modulus of x minus 2 is going to be less and strictly less than 5, where is this now, this particular graph below the line 5? Well, we can see that that is going to be just here. So we can now say, if I wanted to find the values that satisfy that inequality, we could say now that x is going to be strictly now greater than minus 3, yet in turn strictly less than 7. So that shows how we could solve now an inequality. So we've done this now by squaring both sides, and then we've looked at graphing. Okay, let's now look at another scenario. Say we had an equation now, and we had the modulus of x minus 2 is equal to x minus 3. The right hand side is not always positive, therefore we can't square both sides and use the algebraic method. What I want to do is just look at this. Now if we have the modulus of x minus 2, we're going to have a gradient here of 1. This is going to be the point 2, and then we're going to reflect like so. So this now is the line, and we'll put it just here. Let's put y is equal to the modulus of x minus 2. Now if I went ahead and drew the line, let's go ahead and do that. We've got now the line here, x minus 3. We can see the gradients are equal, and we can see that they are never going to intersect. So we've got no valid solutions for this. Yet if I squared this, I'd have x minus 2 all squared is equal to x minus 3 all squared. So I'm squaring both sides. X squared minus 4x plus 4 would be equal to x squared minus 6x plus 9. So the x squared is going to drop off, adding 6x to both sides and subtracting 4, 2x is going to be equal to 5, and x will be equal to 5 over 2. Now if we consider 5 over 2, this point here is 2, this point is 3. This is called what we say is an extraneous solution, and it's considering that now we've got the modulus of x minus 3 and we've got this positive value. Another way to think about this is two parabolas. So if we consider squaring both of these, what we would have now, and I'll just sketch these up, are two parabolas. So as you can see now, we can't go ahead and just square both sides. We end up now with the potential of having more solutions than there are. So if I just now graph these up, what we'd have the same, let's put these here. These now are going to be, this is going to be x minus 2 all squared, this is going to be x minus 3 all squared, and we could see that we're going to have this point of intersection. This is 2 and this is 3, and that's where our 2.5 is coming from. But you can see quite clearly that this is not always positive, therefore we can't use that approach. So instead, what we can do is a purely graphical method. So let's go ahead and look at an example. So let's choose now, let's say we've got the modulus of 2x minus 5 is going to be equal to x minus 1. So on the right hand side we can see now that this isn't always going to be positive. So we can't just go ahead and square both sides, so we need a graphical approach. So what I'm going to do is draw now x minus 1. Let's put on here x minus 1. Remember, this doesn't have to be wildly accurate, it just has to give us some idea of what we're doing. So what we've got then are the following points. This is going to be now 1, 0, so let's put 1, 0 on there, and this is going to be now 0, and then we can have minus 1. If I draw this line now, what we've got is a positive branch and a negative branch. And if we have this now, that's going to be 2.5, 5 over 2, and it'll look something like this, okay? And we'll have something doing like so. So whilst that's not massively accurate, it gives you some idea of what we've got. So we'll now look, and let's just extend that out, it'll look something like that. So we've got now the following. This is the line y is equal to x minus 1. We've got this point just here, which is 5 over 2 comma 0, and now this is y is equal to the modulus of 2x minus 5. So with this one now, we've reflected anything negative in the positive direction. So before we would have had something coming down here. And I appreciate that's not hugely accurate, but it gives us some idea. Now let's look at this closely. We can see we've got a point of intersection here, and we've got a point of intersection here. This now is the negative branch. So this is a negative branch, so we got y is equal to minus the quantity 2x minus 5. And this now is the positive branch, y is equal to positive 2x minus 5. So what I want to do is solve for this one, which I'm going to call now solution 1, and this one, which I'm going to call solution 2. If we look at this one, this line is always going to stay as it is. Now if we have the modulus of x minus some constant, then we would have 2 points of intersection, and we might have to consider now the point where this was negative, but this is always going to be positive. So if we look now at solution 1, we've got now the intersection of x minus 1 with minus the quantity 2x minus 1. So what we can say is minus 2x minus 5 will be equal now, so minus 2x minus 5 will be equal now to x minus 1. If we look at this one right here, which I'm going to call solution number 2, we've got now the positive part. This is the positive part, or the positive leg of the curve. So we've got this part, and this is going to be 2x minus 5, and that will be equal now to x minus 1, so that's the point of intersection. So let's go ahead and solve. So we're going to have minus 2x plus 5 is equal now to x minus 1. Adding 1 to both sides and adding 2x. What we're going to have, 3x is going to be equal to 6, so x is going to be equal to 2. So this point right here, we've got now x is equal to 2. So that's now the point of intersection with the negative leg, or negative branch, and now the line. Let's go ahead and look at this one. If I now subtract x from both sides and then add now the 5, x is going to be equal to 4. And that corresponds to this value right here. So x is going to be equal to 4. So we've got our two solutions. Now do they work? Let's try them. We've got x is equal to 2 and x is equal to 4. So if I sub 2 in, we've got 2 times 2, which is 4, minus now 5. That's going to give me minus 1. So the modulus of minus 1 is going to be 1. Is that equal to 2 minus 1? Yes, it is, so it works. Let's now take 4. 2 lots of 4 is 8, minus 5 is 3. The modulus of 3 is 3. 4 minus 1 is 3. Both of those work, and they are our solutions. So all we've done is looked at graphing. We've considered now the negative branch, and then we have now the positive branch. So what would we do if, for example, we had now the modulus of 2x minus 5 is going to be now less or equal than x minus 1? Well, we would solve the same But all we would consider now is where is my graph, and let's put this on, where is my graph going to be below the line? It's going to be below the line here. We can see now that the line is above the graph, so we would simply go ahead now and say that this was going to be the solutions. We're going to have x will be greater or equal than 2, and in return less or equal than 4. And of course, if we wanted to go where is it more, we would say now that x is going to be greater or equal than 4, or less or equal than now positive 2. So that's solving an inequality. So we can see squaring both sides of this would have given us what we call, or potentially given us, extraneous solutions. They are solutions that hold for the algebra, but in reality don't give us what we want. Often it's the case when you're looking at finding the area of a rectangle that's given in terms of an algebraic expression, you end up with a negative answer. It satisfies the algebra but doesn't satisfy the problem we have at hand. Okay, so there are some basics. Let's move on and look at something slightly more challenging. Let's go for a different one. Let's say we've got the modulus. Let's go for the modulus of x plus 3 will be equal now to 2 lots of the modulus of x. Now we can say that both sides of this are going to be positive. So we could take the algebraic route, and let's go both ways. So if we square both sides, we've got x plus 3 all squared will be equal to, now squaring the 2, that's going to give me 4, and then we're going to have x squared. So expanding out, we're going to have x squared plus 6x plus 9 will be equal to 4x squared. So we're going to have now 0 will be equal to, subtracting x squared from both sides, 3x squared minus 6x and then minus 9. We can split this now by 3, x squared minus, and then what are we going to have on here? Minus 2x, and then we're going to have now plus, what's that going to say? Minus 3. So if we factor this, we're going to have x minus 3, and then we're going to have x plus 1 is equal to 0. So from this we can see now that x would be equal to either minus 1 or x would be equal to 3. Am I happy with those? Well, let's check them. Minus 1 in here is going to give us 2, and that will give us now 2. The modulus of 2 is 2. If I put minus 1 in here, the modulus of minus 1 is 1. 2 lots of minus 1 modded is going to give us 2. That works. If I now put 3 in, 3 plus 3 is 6. That works. Put it in here. That works too. So they are my solutions. Let's say I wanted to graph this instead. Let's say I wasn't convinced that squaring it was ideal. Let's look first at this one while we've got some free space on the graph. We know that the modulus of x looks something like this. So we have these two branches. We have y is equal to x and y is equal to minus x. This is simply a scale factor stretch of 2. So all we're going to do is now crank this up and do something like that. So that now is y is equal to, and I'll put it just here, y is equal to 2 lots of the modulus of x. So all I've done is put a scale factor stretch of 2 on. If we now look at the modulus of x plus 3, what we're going to end up having now is the following. So let's put it just here. We're going to have a gradient that's half as steep, and we're going to have something that looks like that. Okay, so this point is going to be minus 3, so let's put that on. So we're going to have minus 3 just here. Now again, we can see we've got these points of intersection. We've got now the positive branch. This now is the positive branch. This is y is equal to x plus 3. This now is y is equal to minus the quantity x plus 3. This one right here is going to give me now y is equal to 2x. So this is a positive branch here. This is a positive branch of now the modulus of x minus 3. This is the negative branch of the modulus of x plus 3, and this now is the negative branch of now the 2 lots of the modulus of x. So this is y is equal to minus 2x. So let's look at our points of intersection. Let's call this intersection 1. Let's call this now intersection 2. So this doesn't have to be hugely accurate, but it will give us some idea. So let's solve for 1. We've got now minus 2x will be equal to x plus 3. So I'm looking at the negative branch with the positive part right here. If we look now at 2, I've got the positive 2x, so it's 2x, and that will be equal to x plus 3. So we've got those points right here. So solving here, we can see the following. If I add 2x to both sides and subtract 3, I've got minus now, what's that going to give me? Minus 3 is equal to 3x, and minus 1 will be equal to x. And of course, that corresponds, and let's put that there, x is minus 1. That corresponds to this one here. If we look at this one, if we subtract x from both sides, x is going to be equal to 3, and we can see that that's just there. So I've done it algebraically and I've done it graphically. I've checked my answers now and it works, and we can see now that this gives rise to exactly the same answers. So straight off we can see this is good to go, and also because we got both sides being positive, we can go ahead now and simply square this. Okay, let's finish with something that's potentially beyond the scope of what you might be asked to do, but it's quite interesting all the same. Let's choose a quadratic. Let's go for now, let's say we've got the modulus of x squared. Let's go for plus 4x minus 12 is going to be strictly less now than 9. Now with this one, again, we've got lots of different approaches that we could think about doing. What I'm going to look at doing is factoring this first. So let's go for what we're going to have, x plus 6, and then we're going to have now x, and then we'll have x minus 2. Okay, and that's going to be strictly less than 9. So what I'm going to do is draw two graphs, and I'm going to do this purely graphically. So what we're going to have is the following. We're going to have a parabola. We're going to have this quadratic. We're going to have a point now at, let's say, negative 6 is just there, and positive 2 is just here. So we're going to have something that comes around like so, and then comes back up and through. So this is going to be the point now, positive 2, and this is going to be the point negative 6. So we've got positive 2 just here, and then we've got negative 6. If I extend this up, now we've got this line just here, and this is going to be y is equal to 9. So let's go ahead now and draw this. So what we've got now is y is equal to 9, and we'll put it just here. If we think about this right now, what we're going to have is the following. This is the original curve, but I want now the modulus. So if I consider the modulus is going to come down like so, and then we're going to reflect now in the x-axis, and it will come back down, and it will come somewhere like that. Now that will be here. We'll have those cusps which we don't smooth out, and it will do something like that. Now if we look at the original quadratic, this was the point 0, minus 12. So this point is going to be 0, 12. This is going to be y is equal to 9. This is going to be the positive part. This is going to be the positive part. This is going to be the negative part. And this is going to be the negative part. So what we have here is the following. This is going to be x squared plus 4x minus 12. And we'll have exactly the same here. And this one is going to be minus the quantity x squared plus 4x minus 12. So let's see how many points of intersection. We've got one here, we've got one here, we've got one here, we've got one here. I'm just going to get rid of the original curve as we don't want that just here. Okay, that's not part of what we're doing. So what we want to know now is where is the curve below the line of 9. So let's just put this back on here. So what we're interested in now, if we think about it, is this part right here, and then we're going to have this part right here. So what we're going to have are the following solutions. And I'll just put these on. We're going to have now, and I'll call this one solution number 1. I will call this one solution number 2. I'll call this one solution number 3, and this one solution number 4. So if we think about 1 and 2, let's just put 1 and 2 just here. What we have is the positive quadratic, x squared plus 4x minus 12, will be equal to 9. So we've got x squared plus 4x minus 12 is equal now to 9. If we think about the other ones, which I've determined now, or called 3 and 4, we've got now minus x squared minus 4x, and then we got plus 12 is equal to 9. So what we want to do is go ahead and solve them. So let's go ahead and solve this, subtracting 9 from both sides. X squared plus 4x minus 21 is equal to 0. That's going to factor x plus 7, then we're going to have x minus 3 is equal to 0. So x will be equal to minus 7, and then x will be equal to 3. So what we can see by the graph, that this is the point now, x is going to be minus 7. So we got 1 is x is equal to minus 7. This one just here is going to be x is equal now to 3. So there are 2 points. That's 1 and 2. So we got 1 and 2, and let's just put these here. So that's 1 and 2. Let's consider this one right here. So now if I just take everything over to the right hand side, we're going to have x squared plus 4x, and then we're going to have now, that's going to give me, what are we going to have? Minus 3 is equal to 0. Now, that's not going to factor, so I need to complete the square, or use a quadratic equation. Let's complete the square. X plus 2 all squared, minus 4, and then minus 3. So we could write this now as x plus 2 all squared is equal to 7. So we could say now that x will be equal to minus 2 plus or minus the square root of 7. So that gives us 3 and 4. So this one right here is going to be minus 2. So we're going to, let's put x is equal to minus 2 minus root 7. Okay, and this one right here, which is going to be number 4, x is going to be equal to minus 2 plus root 7. So we found these points. So if we were just saying where is it equal to, that's where it is. We want to know where it's going to be less than. So if we think about this now, we're going to have that x is going to be now strictly, and it's a strict inequality, going to be greater than negative 7, yet in turn less than minus 2 minus root 7, or we're going to have now x is going to be between these points right here, which is going to give me my solutions here, which we ought to be 3. So x is going to be now strictly greater than 3, yet in turn now, 3 is going to be this side, isn't it? 3 is going to be strictly less, x is going to be strictly less or equal, less and strictly less than 3, or in turn, now we've got minus 2 plus root 7. So that solves that inequality, and as stated, that one is slightly harder, but hopefully it gives you some idea that going ahead with this approach now allows us to simply solve for these 4 points of intersection, and then consider now where this particular quadratic is below the line. We can see it's below the line in these points here, so I found the points, and by a bit of logic and deciding which one is which, it wasn't too hard with that one, that we've seen that it's going to be this point and this point right here, and there now are the regions that satisfy that particular inequality. So as stated, this will come on potentially a slightly more advanced course, but it's certainly something that isn't out of this world. So there we go, a brief introduction to the modulus function. We've looked at what the modulus function is, we've looked at graphing, we've looked at 2 different types of graphs, and then we've gone on to solve equations and inequalities.